Welcome to This Explainer. Today, we're going to be acting as cosmic detectives. We're setting out to reverse engineer the astrophysics of the modern sci-fi masterpiece, Interstellar, using cold, hard math. We're going to look right past the Hollywood magic and crunch the numbers to see exactly where the science holds up and where the director maybe had to bend the laws of the universe just a bit for the sake of a killer story.
The universe is 13.8 billion years old, vast, ancient, and mostly invisible. And somewhere out there are answers to questions that keep scientists awake at night. Welcome to our channel, where we explore the darkest corners of the cosmos, the mysteries, the threats, the unknown. This is space like you've never seen it before.
Here is our mission itinerary for today. We'll be leaving Earth behind, traversing the wormhole, digging into waves and time dilation, simulating Gargantua, surviving the singularity, and finally building Cooper's Station. Basically, this is our flight plan for an investigative road trip, starting from a dying Earth, traveling right through a wormhole, diving into the heart of a black hole, and ending up at humanity's new home. All right, Section 1, Leaving Earth Behind. Our very first stop is checking the math on the speed and size of the Endurance spacecraft as humanity makes its desperate escape. Let's see if the start of this journey actually makes logical sense. So to reach the wormhole out near Saturn, the crew goes into hibernation for 2 years. But is that timeline actually legit? Well, if we take the shortest straight line between Earth and Saturn, calculating their orbital radii, the ship has to travel roughly 1.3 billion kilometers. Divide that by 2 years, and you get an average speed of around 70,000 kilometers per hour. When you anchor that against our real-world record, which was the Apollo 10 manned flight hitting 40,000 kilometers per hour, it makes perfect sense that a slightly more advanced, near-future spacecraft could absolutely hit 70,000. Now, what about the ship itself? The crew needs artificial gravity to survive, right? So the Endurance spins like a giant wheel, using centrifugal force to push everyone against the outer walls. Just by watching the movie and timing the ship's rotation, it takes exactly 11.4 seconds to complete one full spin. To generate the equivalent of Earth's 9.8 meters per second squared of gravity at that specific rotation speed, we can mathematically deduce the ship's size. It turns out the Endurance must be a very realistic 60 meters in diameter. And honestly, that's totally believable when you consider our own International Space Station is roughly 70 meters across.
Moving right along to Section 2, Traversing the Wormhole. Let's see how director Christopher Nolan and his visual effects team built that absolutely mind-bending three-dimensional distortion of space out near Saturn. To demystify the visual magic here, remember that a wormhole isn't just some flat 2D hole, it's a three-dimensional sphere. And to make it look real, the team didn't just animate it, they actually simulated it. They used the geodesic equation from general relativity alongside a technique called ray tracing. They basically placed a virtual camera in space, shot light rays out of every pixel, and mathematically rewound their trajectories through severely curved spacetime to figure out exactly what color and light would hit the lens. It's quite literally physics driving the pixels. But, they didn't keep it strictly scientifically accurate. In raw physics, if you have a really long wormhole, light can actually orbit inside it multiple times before escaping, meaning a traveler would see infinite, hypnotizing, repeating images of the universe, which sounds incredibly cool. But Nolan shortened the cylinder for pacing. He took a slight artistic liberty with the raw physics just to ensure a quicker, more visually dramatic cinematic transition.
Okay, Section 3, Waves and Time Dilation. We pop safely out of the wormhole right into the territory of a supermassive black hole named Gargantua, and we land on Miller's planet, where extreme astrophysics create a deadly but breathtaking environment.
Miller's planet is this terrifying shallow water world defined by immense 1-kilometer-high waves. And these aren't your normal ocean waves. They're extreme tidal forces caused by the insane gravity of Gargantua pulling harder on one side of the planet than the other. By calculating the gravitational energy required to displace this much water vertically, we can figure out exactly where this planet sits. The math tells us this planet must be orbiting exactly 4.5 billion kilometers from the black hole.
Now, here is where we find an incredible tension in the movie script. Remember the terrifying stakes? 1 hour on this planet equals 7 years on Earth. That's a massive time dilation factor of 60,000. But if we take that orbital distance of 4.5 billion kilometers we just calculated and apply it to a standard static black hole, we literally only get a 5% time slip, meaning initially the movie's math completely falls apart.
So, how do we fix it? How do we hit this massive factor of 60,000? Well, general relativity offers a really neat loophole here. Black holes can spin, and the faster they spin, the closer a planet can safely orbit without getting swallowed up. To actually hit that 60,000 time dilation factor shown in the film, the math demands that Gargantua must be spinning at just a trillionth of a percent slower than the speed of light. It's theoretically possible, incredibly extreme, and completely mathematically justifies the heartbreaking time loss the crew experiences. That brings us to Section 4, Simulating Gargantua. It's time to dig into the stunning visual representation of the black hole itself, widely considered one of the most accurate depictions ever put on screen. Even with all that accuracy, compromises had to be made. Nolan deliberately chose a few visual simplifications to make the spinning black hole less confusing and, frankly, less instantly lethal for the narrative. Raw physics dictates that the glowing accretion disk spinning around the black hole should be subjected to the Doppler effect, so the side spinning toward us should be intensely bright and blue, while the side spinning away should be dark and red. Nolan removed this for a cleaner, more symmetrical look. Furthermore, a real accretion disk is blindingly hot and emits instant, deadly radiation that would obliterate the ship. So, for the sake of the story, its temperature was drastically lowered. While the crew is out facing these physical extremes in space, back on Earth, Professor Brand is frantically filling blackboards with complex equations trying to solve the gravity problem. His work relies on brain cosmology. He theorizes that our whole three-dimensional universe is just a brain, like a slice, sandwiched inside a much larger, multi-dimensional space. The geometry of this larger space, known as anti-de Sitter geometry, heavily bends it all, which confines gravity so it behaves normally in our everyday world. But crucially, this model explains those strange gravitational anomalies back on Earth. It proves that gravity is the only force that can actually leak through these extra dimensions from outside our universe. All right, Section 5, Surviving the Singularity. This is the climax. Let's look at the most speculative part of our explainer and figure out how Cooper actually manages a desperate dive right into the center of a black hole without being instantly spaghettified by gravity. What's amazing is that our real-world understanding of physics evolved just in time for this movie. Back in the 60s, scientists thought a black hole's center was just a point-like singularity that would absolutely crush you instantly. Over the decades, models got a lot more complex, featuring chaotic distortions and crushing walls of piled-up matter. But just a few years before the movie came out, in the 2010s, physicists theorized that extremely old, rapidly spinning black holes might contain a third type of singularity entirely, a gentle singularity. This provided the exact theoretical loophole Cooper needed to survive, provided he flew in at nearly the speed of light. Once inside this gentle singularity, Cooper is miraculously saved by the tesseract, a true four-dimensional cube. Just imagine a standard cube where every single face is itself an entire three-dimensional cube. This structure basically lifts Cooper into that anti-de Sitter space Brand was theorizing about earlier, where vast cosmic distances contract. Now, light can't travel backward in time here, but remember our rule. Gravity can propagate through all dimensions. So Cooper uses the very physics his daughter Murphy needed, pushing physical objects and altering gravity to send quantum data backward in time, crossing dimensional barriers right into her childhood bedroom. Armed with those quantum secrets, Murphy solves the gravity equation back on Earth, allowing humanity to finally lift off. And that brings us to our final cosmic investigation, Section 6, Building Cooper Station. We can actually reverse engineer the hidden architecture of humanity's new home by looking at a simple, casual baseball throw that happens inside this massive space centrifuge. When a kid hits a baseball in this station, it flies in this weird, curved trajectory because the entire station is spinning. By timing the ball's flight at exactly 4.66 seconds and estimating its initial speed at about 30 meters per second based on the batter's height, we can actually calculate the size of the entire station. The physics dictates that to maintain an Earth-like gravity environment with that exact baseball trajectory, the station has to be roughly 100 meters in diameter, and it needs to generate that gravity by rotating exactly 4 revolutions per minute. It's actually a relatively small station, which totally explains why playing a game of baseball in there looks so chaotic. And just like that, we're at the end of our journey. We've seen exactly how a massive Hollywood blockbuster leaned heavily on legitimate, complex astrophysics, from the geodesic equations forming the wormhole to the exact spin rate of a black hole dictating time dilation, right down to the dimensions of a spinning space station. So, here's a question for you to ponder. Will we ever unlock the true secrets of quantum gravity and extra dimensions? Or, for now, are we already communicating across space and time through the gravity of our own art? Thanks for exploring the math with me today in this explainer. Keep looking up.
The universe doesn't care about us. It never did. But we care about it. And that is what makes us extraordinary. If this video made you think, hit like, share it, and subscribe to this channel. Because the next mystery is even deeper. Until then, stay curious and keep looking up.